Hello students, welcome to this new video. Now in this video we will now start studying a new chapter on radiation heat transfer. So this is we have seen in this complete semester we are supposed to study 3 modes of heat transfer, out of which 2 modes of heat transfer is almost covered, that is conduction heat transfer and convective heat transfer. So the last mode of heat transfer is what is called as radiation mode of heat transfer, which is a very important mode of heat transfer. Basically many applications in our real life involve radiations, and of course the heat transfer is also involved with respect to radiation is concerned. Now in this video we'll try to understand the basic concepts of radiation before actually getting into radiation heat transfer. So let me be very specific here. There are two words here, two different types of subject here. Radiation is one different and heat transfer is one different. So first we'll try to understand the basic concepts of radiation, then we will move on to understand the heat transfer through radiation. Understood? So most of the initial videos will be on understanding the radiation, then we will try to understand how the heat transfer takes place through radiation. Understood? So more or less it will take hardly 2 to 3 videos, only basic concepts I'll be able to give you. Now what is radiation actually? So if you see conduction mode of heat transfer or convective mode of heat transfer, we need a medium for the heat to transfer, correct? So in case of conduction mode of heat transfer, we need, so let me just brief here. For conduction mode of heat transfer, we need a medium for conduction as well as convection. We need a medium. So whereas in conduction it is a solid medium, in convection it is a liquid medium. So whereas actually convection, the liquid medium should have a dynamics involved in it. So for radiation mode of heat transfer, you don't need a medium for the heat to transfer. Meaning to say that it's not that if medium is there, radiation will not take place, of course. So it is not a mandatory thing. That means to say even there is no medium, that means to say even if there is no air, even in vacuum also it is going to transfer. Got it? Through radiation. Now that is what the radiation mode of heat transfer is. Now we will understand what is actually the radiation. So what is this? Radiation heat transfer is defined as, please read it. Radiation heat transfer is defined as the transfer of energy across a system boundary by means of an electromagnetic mechanism which is caused solely by a temperature difference. Suppose say there are two bodies, let me just draw it here, body A and body B. This is maintained at T1, this is maintained at T2, and this is separated by a certain distance, and here suppose say there is no medium, so vacuum is, so the energy is going to transfer from body 1 to body B, that is body A to body B, through what is the mode? Through radiation. Actually the heat is being transferred, and the mode, what is this? How the energy transfer takes place through radiation? Through electromagnetic waves. So the radiation, by means of electromagnetic waves, the radiation is going to take place. So this is what is called as radiation. A radiation involves what? Electromagnetic waves. So as soon as we say wave, what are the two things that comes into picture with respect to wave is concerned? That is wavelength, which is denoted as lambda, and then frequency, that is f. So what is this? V is equal to f lambda. You have studied this already. So these are the two things. As soon as we say wave, what is the wavelength and what is the frequency. That is what people will try to, so which is denoted as hertz. Correct? Now let us now try to understand the band where different types of waves are fall into based on the wavelength. Now this is what the wavelength in terms of micrometer this is. Now if you try to see, here it is RHS, it is positive side, that is positive in the sense 1, 10, 100, 10 to the power of 3, 10 to the power of 4. Here it is 0.1, point like that it is going to be 10 to the power of minus 1, 2, 3, 4, 5 like that. So if you observe here the thermal radiation, whatever that the topic that we are concerned, the thermal radiation lies between 10 to the power of minus 1, that is 100. 10 to the power of minus 1 is, sorry, 10, yeah, it is 10 to the power of minus 1. So 1 by 10, correct? So 1 by 10 is 0.1. So 0.1. So 10 to the power of minus 1 to 10 square, that is 10 to the power of 2. So the thermal radiation lies between 10 to the power of minus 1 to 10 to the power of 2. Within this thermal radiation, actually, the visible spectrum lies between what and what? The visible spectrum lies between 0.4 to 0.7. Please be aware of it. The visible spectrum lies between 0.4 to 0.7 micrometer. Understood? Now if you see the infrared, now we will try to see after 10 to the power of 2 what is called as microwave, and after this 0.7, between 10 to the power of 2 to 0.7 is what is called as infrared. Now 10 to the power of 0.4 onwards, that is till 10 to the power of minus 2, it is ultraviolet micrometer, and beyond 10 to the power of minus 2 this is what is called as X-rays, and between 10 to the power of minus 4 and minus 3 and onwards it is what is called as gamma rays. So this is what a brief map, or I can say brief spectrum of waves, where different types of waves rays is going to fall back. Here most important thing which you should not forget is what is called as thermal radiation, which lies between what? 10 to the power of minus 1 to 10 to the power of 2. So please don't forget that, within which the visible spectrum lies between 0.4 to 0.7 micrometer. Understood? So this is what the thing is. Now very slowly we will try to understand many concepts related to radiation. Now why bodies emit radiation? Why actually, suppose say you have a body here, so maintain that temperature. So why bodies emit radiation, or when do bodies stop emitting radiation? Body emit radiation. So all bodies having certain temperature is going to emit radiation. So if a body is maintained at say temperature T, it is going to emit radiation in all directions. So please be aware of this. Any body maintained at temperature is going to emit radiations in all directions. So that is why we will try to give name as, so since it is emitting radiation in all directions, it can be enclosed inside a hemisphere. It can be enclosed inside a hemisphere, and since it is emitting in all directions, it is hemisphere, and every wavelength, that means it is going to emit for every wavelength there is this radiation. So there is this definition called as monochromatic, hemispherical, emissive power. Monochromatic, hemispherical, emissive power. Now what is this monochromatic, hemispherical, emissive power? Let us going to define in a very very short span of time. Monochromatic refers to what? Certain wavelength. For a particular wavelength, what is the emissive power? Hemispherical denotes what? Direction. Emissive power is what is the power? What is the range? How much is the power? How much radiation is being emitted? Now how do we define? This monochromatic, hemispherical, emissive power? It is defined as total amount of radiation total amount of radiation emitted by a body per unit area and time. Total amount of radiation emitted by a body per unit area and time. Now, with respect to this, there is two more other terms which is going to fill into per unit area, total amount of, so amount of radiation emitted for a given particular wavelength lambda in all direction by a body per unit area per unit time. So that is what is called as monochromatic hemispherical emissive power. So this is denoted as E lambda. Are you able to understand? E lambda. E lambda denotes what? Monochromatic hemispherical emissive power. Now, what do you mean by there is one more term comes into picture? Now, for a given wavelength, what is the amount of radiation that is being emitted? So you need to consider for a given wavelength what is the amount of radiation emitted in all direction. So that is why this word hemispherical. Now, how do we define total emissive power? Total emissive power is also defined. That means if we try to add up all the wavelengths, that means radiation emitted by all the wavelengths, then it is called as total emissive power. So your total emissive power is denoted as E is equal to integral 0 to infinity, means whatever the different types of wavelength you have for all the things, E lambda d lambda watt per meter square. Are you able to understand? So this is total, this is monochromatic. Are you able to understand? So what is the difference between total and monochromatic? Monochromatic for a given wavelength, total. So what is that means? So where does the word spherical goes? So the spherical is understood. So if we are saying the radiation is emitted, so that is why people don't always attach the word hemispherical. It is understood that the radiations will be emitted in all the directions. So suppose say you have a body, it is understood that radiation is emitted in all the directions which can be encompassed inside the hemisphere. Are you able to understand? So people, it is understood that we don't use this hemispherical always. So monochromatic emissive power and total emissive power, like that we are going to say. It is understood that it is hemispherical. Okay, it consists of all directions. So what is this? This you should not forget. What is this? Total emissive power E is equal to what? Integral 0 to infinity E lambda d lambda watt per meter square. Now with respect to black body, now we'll define what is that black body in the later stage. Now this is what is called as monochromatic hemispherical emissive power and total emissive power. I think you understood, correct? Next thing is we will define what is called as emissivity. Now how do we define this emissivity? Now before actually defining this emissivity, how do we define emissive power? No, we did not define emissive power, right? How do we find out? Suppose a body is there which is maintained at temperature T, which is emitting radiations in all the directions, correct? So how do we find out what is the energy that has been dissipated through radiation? Suppose say let us consider this is the black body. So it is been given by a Stefan-Boltzmann law. Using Stefan-Boltzmann law. So if any body is there, so how do we find out that? For a black body, the emissive power of a black body EB is equal to, first of all, it is directly proportional to t to the power of 4. Now if you try to remove this proportionality constant, it is going to, you have to introduce a constant epsilon a t to the power of 4 watts. So this is what it turns out to be. Are you able to understand? This is the units. So this is the emissive power of a black body. This subscript B denotes what? Emissive power of a black body. Now how do we define emissivity? So emissivity is denoted with the help of epsilon. So emissivity is a surface property which is defined as, which is a ratio of emissive power of any body and emissive power of a ratio of emissive power of any body with respect to ratio of and emissive power of a black body. That means to say you have two bodies. Suppose say this is some say gray body, this is say black body. Suppose say this is emitting radiation, has a certain Eg, this also emitting radiation, this black body which is denoted as Eb. So the emissivity epsilon is defined as emissive power of gray body, emissive power of a black body. Are you able to understand? So E divided by Eb, Eg divided by Eb, or now it need not be gray body, any body for that matter, correct? Any body for that matter. So epsilon is given as any emissive power of any body considered divided by emissive power of a black body. So it is very quite natural that always the emissive power at a given temperature, for a given temperature, emissive power of a black body always will be higher than any other body. So always epsilon will be less than 1 for any given body compared to black body. So this is what the definition for emissivity. So emissivity is a surface property. Emissivity is a surface property. Emissivity is a surface property and emissivity, so epsilon equal to 1 for black body. So epsilon equal to 1 for a black body. So this is what you need to understand for emissivity of a black body. Understood? Now let us try to understand 3 more concepts. Now suppose say consider some body is there and there is this incident radiation which is falling on this body. Some of the radiation is absorbed and some of the radiation is actually transversed and some of the radiation is actually reflected out. So this is what is called as the radiation which is incidenting on the body, on the surface. So this is the body actually. So this is what is called as incident radiation. Let us consider there is a certain radiation is falling on the body. So it is written as incident radiation, which is denoted as G. So there is some amount of radiation which is falling on the body. That radiation, some of the radiation is absorbed and some of the radiation is allowed to pass through this, transmitted, absorbed, reflected. That means part of this radiation which is incidenting on the body is absorbed into the body and some of part of this incident radiation is transmitted through the body and part of this incident radiation is reflected out of the body. or from the body. Now this is what is denoted as, say, reflected radiation. And this is called as transmitted radiation. Transmitted radiation, and this is whatever that is absorbed, and I'm writing it here, absorbed radiation. So this, let us try to give the name it as GR, which is reflected, absorbed, which is GA, and this, let us try to give it as transmitted GT. Now shall we try to apply a simple formula here? So whatever the incident radiation G is equal to what? GR plus GA plus GT. Correct? GA, GT. Now dividing both sides by G, if you try to do G, so which is equal to what? So let me just write it like this. GA by G, let me take this first, then GR by G plus GT by G, which is equal to what? 1. Correct? Now this has a certain terminology which is associated with this. GA by G, the ratio of the total incident radiation, like the absorbed versus total, is what is called as alpha plus rho plus tau, which is equal to 1, where your alpha is what is called as absorptivity, rho is what is called as reflectivity, and tau is what is called as transmittivity. So this you need to understand. So for a perfect black body, now what do you mean by a black body? How do we define a black body? Now black body is that body, suppose this is a black body. If we want to call this as a black body, how do we say this is a black body? If some radiation is falling on it, first of all, it absorbs all the radiation. It actually allows all the radiation to go here. It will not just simply allow all the radiation, it will absorb. All the radiation gets absorbed inside the black body. So that is the reason it is called as a black body. Understood? So for a black body, which are the things that is 0? It will never allow any radiation to pass through it. So transmittivity is 0. Yes or no? So tau will become 0. And it will not allow any other radiation to reflect back. So what is 0? Your rho is also become 0. So therefore, which is equal to 1? Your tau alpha will be equal to 1 for a black body. So black body is that body which absorbs all the radiation. It will allow all the radiation to go through that. It is not enough, but still it will absorb all the radiations which is fallen into it. So your alpha is equal to 1 for a black body. Now what do you mean by an opaque body? Your opaque body means to say it will not allow your tau is equal to 0. So therefore alpha plus rho equal to 1 for a opaque body. For white body, what is that for a white body? For a white body, it will reflect, yes or no? It will not absorb, it will reflect all the radiations. So your alpha is equal to 0, your tau is equal to 0, therefore your rho is equal to 1 for a black body. Are you able to understand? So this is what the first part of the basic concepts. So in the next video, we will try to see different laws with respect to radiation is concerned. Okay, thank you.